Hi, SPU 30. It's me, Peter Hedman, and I'm here to answer the question, what evidence supports the crazy notion of plate tectonics? Today, we are pretty convinced that the Earth's crust is made of large plates or pieces that move very slowly and rearrange themselves over geologic time. The evidence for this can be very direct. Today, we can use GPS satellites to measure the motion of these plates, and we find that they tend to move about as quickly as your fingernails might grow. But to understand how the Earth works, we have to consider what other evidence we see on the planet. Here is a map of the Earth. This is a map of the topography, all the mountain ranges on land, and the bathymetry of the ocean. And we see the Earth's crust seems to be made of two different sorts of plates. There are these thicker continental plates that make up the dry land of the planet. And you can see that they're also flooded in certain places. And then there are thinner, denser plates that make up the ocean basins of the world. They are usually filled in with water because they're lower. They're lower topographic relief on the Earth. What I've highlighted here in the middle of the Atlantic Ocean is a mountain range, which stretches all the way from the north to the south. These mid-ocean ridges are actually the longest mountain ranges on Earth, and what they represent is new oceanic crust being created as the plates pull apart. So if we zoom in, we can take a look at this a bit more closely. So you can see that at the mid-ocean ridges, crust is being pulled apart, and volcanoes erupt, creating new oceanic crust. This is a divergent boundary where new crust is being created. Let's find another type of boundary on the surface of the Earth. Zoom out. As you probably know, if we move to Japan, we will be able to see a subduction zone. This is a place where the oceanic crust dives underneath the continental crust. So here the oceanic crust dives underneath the continental crust. Japan is actually a continent in creation. It's being made right now. So looking at the large-scale picture of the Earth's crust, we see there are regions where crust is being produced and regions where it's being destroyed. This is why, on average, the ocean basins are quite young, because the oldest bits of the ocean have already been destroyed. So what drives this process? What energy source could move around large chunks of the Earth's surface? To understand that, let's look at a cross-section of the planet. So, from seismic wave studies, we know that the Earth has a solid inner core and a molten outer core. And what is the inner core made of? Well, it's made of iron and nickel. Remember, those iron-nickel meteorites are thought to be the cores of other planets. And so those are the sort of pieces of evidence that let us figure out what our planet's core might be made of. And then around the inner core is a liquid outer core. Imagine that's round, if you will. And then above the liquid outer core is the mantle. And this is the rocky part of the Earth that makes up most of the volume and structure of the Earth. And then on top of the mantle is the crust. And I'm going to draw the two types of crust in a very exaggerated way. First of all, we have the dark, dense crust of the ocean floor, of the ocean basins. And this is called basalt. That's the type of rock that the oceanic crust is made of. And then, by contrast, we have thick continental crust made of granite. So that's what I'm drawing here. Thick continental crust made of granite. And if this oceanic crust ever runs into the continental crust, as we thought about in the case of Japan, it will subduct or dive underneath it. If the continental crust ever runs into other pieces of continental crust, they'll collide together and form mountains. This is what's happening north of India as India collides with Asia and builds up the Himalayas. At certain places, oceanic crust is pulled apart, and new oceanic crust is created at these regions, these divergent boundaries. And sometimes, oceanic crust will collide with oceanic crust, and one of them will dive underneath the other, like this. And this is the process by which you can build new continental crust, because it's the eruption of the volcanoes that occur here that can build new continents. At this subduction zone, there'll be volcanoes which occur on top of the continents, and here there'll be underwater volcanoes that occur to build up new oceanic crust. And so this is the general picture of the motion of the plates that we're familiar with. But what's actually driving the motion? What is the power that powers this Earth system? The source of power is the internal heat of our planet. So you can think of plate tectonics as just being the consequence of our planet cooling down over millions of years. And this is something that Professor Sasloff has mentioned in lecture. Plate tectonics is just our planet cooling down. You might put a hot pot of water on the kitchen counter, and then it will take a couple hours to cool down. But apparently the Earth has taken more than 4.5 billion years to cool down. And so plate tectonics is the manifestation of that process. The Earth's interior is quite hot, and it gets cooler as you move away from the interior. So if you consider a parcel of rock near the, say, core mantle boundary, it's quite hot. And as it's hot, it can expand a bit and it can start to rise, and it will move to the surface. And then it may begin to subduct again and fall back down. So we get these large-scale subduction currents where rock from the center of the Earth moves up, subducts, and then moves back down. This is just like the subduction or the convection currents that occur within hot pots of water, except they occur within the solid mantle of the Earth. So the rock that makes up the mantle of the Earth is not liquid, it's solid, but it can move plastically or deform over millions of years, and that's what gives rise to the plate motions. It's the deformation and movement of this rock in these large-scale convection currents that actually lead to the motion of plates on the surface. And so this is the basic cartoon picture of how our planet works. Plate tectonics is just the manifestation of our cooling planet. So how did the Earth get so hot to begin with? Where did all that energy come from?